solution for few vibration problems, and these are exact solutions of a simplified problem. Let us take this as the fuselage mass, left side, and this is my wing whose length is L, and EI and M are its properties, and this is okay vibrating. And we have developed the equation of motion, and then we applied the separation of variable, and we got the differential eigenvalue problem. So I will write the differential eigenvalue problem along with the boundary conditions directly. So you will get d square over dx square EI d square w, which is a function of x, over d x square equals omega square m w, or which we wrote it as lambda m w, where m is the length, E is the bending stiffness. With the boundary conditions, at x equals 0, we had EI d square w by dx square is 0, and then d over dx of EI d square w by dx square equals m L omega square w, or you can write it as m L lambda w. And at x equals L, we have the other two boundary conditions, which are EI zero and d over dx of EI okay. So we have the four boundary conditions. Now how do we solve the problem? Let us make some approximation. The approximation is EI and M are constants, which means it is a uniform beam. Uniform beam. Okay. When we write it as a uniform beam, then for this we can get the exact solution. I erase this part. Okay. Your equation in the field, it becomes EI d4 w by dx4 equals your lambda m w, which you can write it as d4 w over dx4 minus lambda m over EI. And this particular quantity, we are going to call this as a beta to the power 4. Lambda m over EI. Please understand, lambda is the omega square. So if you want, you can keep that just for okay. Now this is a constant, and this is the fourth order ordinary differential equation. You can write the solution as W of x as C1 sine beta x plus C2 cosine beta x plus C3 sine hyperbolic beta x plus C4 cosine hyperbolic beta. Okay. Now, if you substitute this, you will get this equation is exactly satisfied. Okay. Now, you need to find out these 4 constants C1, C2, C3, C4. Those are, you cannot obtain them uniquely, because what you have to do is you have to take this function, substitute in the 4 boundary conditions. Then you will have 4 equations. Okay. 4 equations. If you bring this, because W is there, so you bring it to the left hand side, you will find that 4 simultaneous equations which you can put them in a matrix form. C1, C2, C3, C4 equals 0. I have to fill up this matrix, that's all. And this will contain beta, because I will finally write that, because when you substitute, because I don't want to differentiate everything. This you can do it by yourself. Write the final matrix form. You have to take second derivative of that at x equal to 0, set it to 0. Then at x is equal to 0, this is the third derivative, set it equal to this. And then like that, you set for all the 4 boundary conditions. What will happen is, you will get an equation of this form, which maybe I will write it in this place, because I have to erase it. This will become, I'll write directly there, applying the boundary conditions, please understand. You will get 0, minus 1, 0, 1, minus 1, minus m L over m beta, 1, minus m L over m beta, and erase this. Then minus sine beta L minus cosine beta L sine hyperbolic beta L and cosine hyperbolic beta L. And the last equation will be minus cosine beta L sine beta L cosine hyperbolic beta L and then sine hyperbolic beta L. C1, C2, C3, C4 equals 0. Okay. Now this is my boundary condition equation. In this, the unknowns are, of course, C1, C2, C3, C4 you do not know, but you also do not know beta. Now, for this to have a non-trivial solution, non-trivial means I should not get C1, C2, C3, C4, 0 is exactly, it will satisfy. You want a non-trivial solution, then you say the determinant of this matrix is 0. And the determinant, this will be a bit lengthy stuff. You have to do numerically only. Okay. I will not be solving the entire thing. Once you set the determinant 0, the only unknown is beta. For what values of beta the determinant is 0? A finite number, but they are all discrete numbers. Then corresponding to each beta, if you substitute that, you can find the eigenvector. Okay, C1, C2, but not all of them will be arbitrary. You have to fix one, because this is a 4 by 4 matrix. If I say C1 can assume any value, then I can write C2 in terms of C1, C3 in terms of C1, C4 in terms of C1. That is a, okay. That means I will go back and substitute the corresponding beta values here and the C1, C2, C3. So every beta value, for every beta, you will have one vector, which is something, you can say 1, some value, maybe alpha, beta, gamma into C1, because I am taking C1 as 1. All the alpha times C1 will be C2, beta times, okay, alpha, beta, everything is beta. Okay, it's all right. It doesn't matter. This is an independent, okay, maybe alpha bar, beta bar, gamma bar. Okay. For every value of this beta, you will get one eigenvector. This vector is not called the eigen, you may call it eigenvector here, but actually this is your beta. If you go and substitute, you will get the corresponding omega, which is the frequency of vibration of the system. You will get the frequency. When you substitute these values here, you will get the deformation. That you call it as a mode shape, or in the current problem, it is the eigenvalue and eigenfunction. Okay. So eigenvalues, eigenfunctions I get, but these are exact, because I have solved a closed form solution. But invariably, I will not be able to get when EI, M are not constants. That part we will learn later. Today we will say in a simplified case, because there is something more in this particular problem, because it is you have only a mass and the beam, and it is free. Okay. You can also have another solution. Please understand, I am deviating. Another solution where W of x equals some constant C0 plus some C1x with lambda 0. Please understand, for the given problem, if my W is of this form with lambda 0, that means then this also satisfies. Not necessarily C0 has to be 0 or C1 has to be 0. These are some constants, or you may call it A0, A1, whatever way you want to call it. Now this particular, they will satisfy the boundary condition also. If you see, boundary conditions are second derivative or third derivative. Anyway, second derivative is 0. Third derivative is with lambda is also 0. This will satisfy the equation as well as the boundary condition. That means this particular shape, that means one is C0, which is a constant. That means the entire system can move up and down uniformly. without with 0. This is a rigid body motion. This you call it rigid body translation when this entire system moves up. Okay, that is this. Rigid body modes have 0 frequency. Okay. Now the other one is a C1x. C1 is a constant. X means as you go along x, the displacement is a function of x, linear function. That means I can have a situation where the mode shape can be like this. This is the rotation. This is translation. This is pure rotation. Okay. I can add both of them. That means this is also a rigid body mode and this is also a rigid body mode. The rigid body modes have 0 frequency. Okay. This is always, this will come only in free system. Free system. Because we have not restricted this system anywhere. It is free to go up and down. Along with this, we have W also. This is W which we said. That W is this. All the points move same, and there is a rotation. Another one. Okay. Then what is this? These are your flexible modes. This is the rigid body mode. This is the, which is a function of x, sine, cosine, sine hyperbolic. They are flexible modes. And the flexible modes will have a corresponding non-zero lambda. Okay. Flexible modes will have non-zero lambda. And essentially your solution consists of some rigid body modes and some flexible modes. Okay. Is it clear? Huh? Is it clear for you? Now we can simplify the problem. Yes. Yes. Okay, now the question is what really happened in the actual system? That is the response problem. Okay. That is the response. What we say now is the differential eigenvalue problem gives me a set of frequencies, a set of deformation, or you may call it shape functions or eigen functions. So I have essentially a frequency. One, I can plot it like this. Frequencies and mode shapes, okay, which is, I can call it eigen function. This is the eigen function. Okay. First frequency, I may say this value is 0. For this is a C naught. Everything is moving up and down. Second frequency, that is also 0. This is C1x. Because second frequency, you may be omega 1, you may omega 2. I'll put it. When I go to omega 3, that is my beta. I have to get it from beta 3. Omega 3 means omega 3 square will be beta 3 something. So I can put it, what is it? It will be omega 3 square if I take it. EI over M and beta some whatever that power 4. Okay. Usually it will be always beta L, they will write some value. Anyway, here you take it. Now from here omega 3 is this value. You know the beta value, you can substitute, you get this. Corresponding to this, you will have some C1 times something sine beta x, beta 3x plus some alpha bar cosine beta 3x plus beta bar. This is another constant. Sine hyperbolic beta x plus alpha beta gamma bar cosine hyperbolic beta 3x. Okay. This is my shape function because C1 I don't know, arbitrary. Like here, this is C0. I don't know how much it will move, but every point will move. C1, I don't know. Here also this is. Like that you can have, you can put it 3 as n. And you can correspondingly this will change. Now you see, corresponding to each natural frequency, you have a corresponding mode shape, or you can say eigenfunction. Okay, this has an exact solution. Even here, exact I said, this you have to solve by numerically, because these are all sine and cosine hyperbolic functions. Okay, you have to solve them numerically. Now, what really is going to happen in the actual situation? Because everything is a solution. So you will go and write your, this is what is called the expansion theorem. This part, I erase this part. This is for just, now my motion can have all these possible. So my W, which is a function of x comma t, I have split them into separation of variable. Wx is all these functions. Okay, and I will simply write here some W n x eta. You can go up to, technically it is up to infinity you have, but n running from 1 to n, that's all. Now you see, this is my general motion, because everything is a solution. Please understand, everything is a possible solution, and you know that these are eigenfunctions and they are orthogonal. Orthogonality condition they will satisfy. You follow? This is called the expansion theorem. Basically, you are expanding your general displacement of the structure in terms of its mode shape or in eigenfunctions. Okay. But these are free vibration problem solutions. Now you have to solve for forced vibration. Forced vibration means there is an external load acting. How do you solve that part? We will come to that later. How do you really? You have to basically substitute this and then use the penalty principle, and you will get now equation 8. Okay. Now I have represented my structural vibration or structural motion in terms of the mode shape, and these are, I call it now generalized coordinates. This I call it generalized coordinate. Okay. These are my mode shapes. Are eigenfunctions. Now you see, it also leads to, how did I get that mode shape? I got the mode shape by solving in this particular case, I was able to solve the problem. Now, if I cannot solve this problem, then you can always say, I make a assumed mode shape. Okay, that means this function you assume it. Okay, but what we got exactly the function which satisfy the boundary conditions as well as the equation. Whereas the mode shape, you have either it can satisfy the equation, it may not satisfy because you don't know, but you can at least make sure that they satisfy the geometric boundary conditions which are admissible functions. Okay, suppose if those functions satisfy geometric as well as the force or natural boundary conditions, then you call them as comparison functions. If it satisfies all the boundary conditions and the equation, then that is eigenfunction. Now you see, we got eigenfunctions for this particular problem, exact eigenfunction for an approximate problem. Okay. Now what I will do is, I will give just, if I make this ML0, how the mode shapes will look. Okay. That is a simplified problem for which you will have the solution in the book. Okay. I erase this part. A simplified case. Further simplified. That's what I am saying. Yeah. Well, it's a little tricky. It should reach that value, but you will still have a rigid body mode. Please understand, because what will happen is the flexible modes will be tending towards that value, but you still have rigid body mode which you cannot, because I have a heavy mass, that doesn't mean, but all can move up and down. Okay, so you cannot remove these two unless you enforce that it is fixed, it cannot move. So don't think that the solution of a cantilever beam is a limit of having ML infinity. You can't truly correct. But the flexible modes will approach that value, but not the rigid body mode will exist as a rigid body. You cannot stop that. Okay? Are you clear? Because it is not that this is a simplified case of the other case, other problem. You have to see physically what can happen. Now let us take this very simple case, ML is 0. Okay. This is like I am having a highly idealized situation of a flying wing. The entire wing is represented as a beam. Okay. Now what are its mode shapes and frequencies? Anyway, rigid body mode will stay. The elastic modes or the flexible mode, that determinant you can simplify and it will become simply like this, because when ML equal to 0 you will get C2 equals C4, and because C1 equals C3. This is the boundary condition. When you substitute the boundary condition, finally you will land up with this type of equation. I am not writing all the steps. Sine hyperbolic beta L cos beta L plus cosine hyperbolic beta L minus cosine beta L plus cosine hyperbolic beta L sine beta L plus sine hyperbolic beta L multiplied by, I am putting C1, C2. This is like a simplified, because C4 is C2, C1 is C3 from the boundary conditions. Okay. Now for a non-trivial solution, the determinant has to be 0. If I multiply, get the determinant, that is your characteristic equation, that will become, I am simplifying, please understand, I am not writing all the steps. Hyperbolic beta L minus 1 is 0. This is my characteristic equation, ML is 0. Okay. Now the solution is simply, this is for a free beam. Free beam is just this beam. How this will vibrate? EIM. That's all. We have done this problem. Simple. Solution of this. Okay. You can get it graphically. Okay. Because you know that cosine beta L is a cosine function. You take it to the right hand side, 1 over cosine hyperbolic. Hyperbolic is exponential function. It will always decrease. Wherever these two cross, they are the solution. Okay. So I will write the solution here. Beta, I may call it 0 is there and 2 zeros are there. So I am calling it as a beta third value. L equals 1.5065 and beta 4 L is 2.5005 and so on. Beta R L, that is any other, is approximately 2R minus 1 over 2 into 5. And your function, this function will be like this. I am going to write here sine beta R x plus sine hyperbolic beta R x plus minus sine beta R L plus sine hyperbolic over cosine beta R L minus cosine hyperbolic beta R L multiplied by cosine beta R x plus cosine hyperbolic beta R. Okay. And your W0, W1, they exist. W0 is some constant C0 and W1 is your some C1x, R running from 3 onwards, because here R goes from 3, 4, 5, etc. So you see, I now have from here the frequencies. Okay, this is my mode shape or eigenfunction, and I can plot. So let me erase this part. Just for simplicity, just for graphical. These are the mode shapes or eigenfunctions. So this is W. So this is my x. So this is constant. This is W0. That is the first mode. Frequency omega 0 is 0. And the second one, I can take it like this. It is a rotation, C1x. Okay. And this is also omega 1 is 0. When I go to the third one, how it will vibrate? It will vibrate like this. This is at L. This is the length L. Okay. Maybe I should plot it nicely. Okay. And for this, the frequency will be 1.506 pi whole square EI over M L4. Because I have taken 1.506, substitute that beta and get the omegas. And the next one will be okay. Here this is omega 3 will be 2.500 pi whole square, again square root of EI over M L4. Okay. And so on and so forth. You can have many like that. So these two are rigid body modes. These are flexible modes. Okay. And your general motion is this. You can substitute n. I put actually starting from 1, even you can start from 0 also. There is nothing wrong because 0 is the rigid body mode. That is 1. Okay. You can start from 0 or 1, that is just a index. But interesting thing here is, in this case, the beam vibrates in a symmetric fashion. Okay. Symmetric in the sense both side will go up. Whereas when you look here, this is not like that. This is an anti-symmetric mode. Okay. So you will have symmetric mode, anti-symmetric mode. Several. If you go to the next one, fourth one, you may get symmetric mode. Okay. It may come down, up, and then go up. So like that, you will have symmetry, anti-symmetric modes. But if you solve in this fashion, you will get exactly everything. Because symmetric mode, anti-symmetric mode, all the modes, what are possible. Okay. On the other hand, if you, that is why when you solve the full wing problem, it is better to solve both sides. If you are solving for a actual flight. Whereas if you restrict half, you are saying, I restrict only 1/2 of the wing, then you need to be sure what boundary condition you set in at the midpoint. Suppose this is my aircraft. Okay. If I cut it, I have half. If I want to analyze only half of the system, I must be clear what boundary condition I set in at the midpoint, because you are analyzing only 1/2 of the system. Okay. If you set a particular type of boundary condition, suppose I say displacement here is 0, slope is 0, right? Then what? I will get only symmetric type of things. Whereas here I allow rotation, but I don't allow displacement. Okay. So you may have to change the boundary condition suitably. Whereas if you solve the full problem as it is, you will get everything fine. Okay. This is just for sample case I did it free because your aircraft is a free system. That's why when you analyze, no, if you, both solutions, then you have to change the boundary condition. No. Here you allow what? If I say this half, I want this is going, slope is 0, and then here curvature is, you set it curvature, displacement I allow, okay. Whereas here you have to take the other way around, some change, displacement is 0, and then I think here curvature is 0, here curvature exists, something like that. Here curvature is 0, here curvature exists. So you have to put curvature, second derivative, you cannot set it 0 here, okay. So that is how you have to be very careful what I allow. Whereas if you solve full problem as it is, you will have everything without any problem. Because this is just to indicate that if you take half the problem, I'm just telling you, you have to be very careful about what boundary condition you are setting it in that one end. Because that will give you only that set of solution. It will not give you the other solution. Okay, that is the reason why, because to avoid that confusion, I solved the full case. In the sense, I said ML0, and that is the full free beam. Okay, and now you know that I can solve any type of problem, because I can have ML here, I can have ML here, both wings, or I can put one mass in the middle, put everything, but boundary condition will be here and here. Some mass is sitting here. That's okay, that will come part of your equation. Okay. Now, if you take the most familiar problem, which is the cantilever problem, that means one end is fixed. I'll write again this part. I erase. No, I thought I will just write the cantilever solution directly. Okay. Maybe I erase this whole thing. The familiar problem of cantilever beam, uniform cantilever. Uniform. Okay. Cantilever uniform beam, if I say, now I don't have rigid body modes because displacement on the left hand is 0, slope is also 0. So your first mode itself will start like this, and your second mode will be like this, and your third mode may go like this. So I will write the corresponding frequencies, that is basically clamped. Here it is 0. This is W. You will have omega 1 is 0.597 pi EI over ML4. Then omega 2 you will have 1.49 pi whole square EI over ML4, and omega 3 is pi over 2 pi EI, like that, so on and so forth. And the interesting part for this, the characteristic equation, I am writing characteristic equation, just for your interest. For cantilever beam, your characteristic equation, which is nothing but your determinant equal to 0, you will get cosine beta L, cosine hyperbolic beta L plus 1 equal to 0. This is for cantilever. In the earlier case, you got minus 1 equal to 0, and your corresponding mode shapes are WR, which is a function of x. This will become again CR sine beta RL minus sine hyperbolic beta RL multiplied by sine beta Rx minus sine hyperbolic beta Rx, and then you also add plus cosine beta RL plus cosine hyperbolic beta RL multiplied by cosine beta Rx minus cosine hyperbolic beta R. Okay, this is this shape. Please understand, this particular function is this. Okay, earlier we plotted the other function. So you find cantilever beam, but the beauty is equation is not changing. What is changing is only boundary conditions are changing. Because of the change in boundary condition, you are getting different frequencies, different shape function, or different eigenfunction. So that is the essence of this. Your field equation may remain the same, but your boundary conditions will completely change the solution. Okay, that is why it is very essential for you to understand this thoroughly, and once you understand this part, then solving any problem. Basically, your aircraft wing is a vibrating system, and you will be able to solve all the problems associated with that. First thing is you must know basics. That is why this is mentioned. Now what I will do is I will take the torsion problem. Similar to what we did for bending, I will take a simple torsion problem, right? Its mode shapes, because they look a little different. Okay. So I completely erase this. I hope you have understood thoroughly. Now let us take the torsion just for completeness sake, because the procedure is identical. Only thing is the equations are different. Okay. Let us take the case of again the wing is represented as a uniform beam of torsional vibration. Okay. Again, free vibration equation, we have this. If you look back your notes, you will have this. Delta phi by delta x equals I p phi double dot. Double dot is second derivative with respect to time, and if it is a fixed, this is Gj and Ip, and this is okay. The corresponding boundary conditions. At x equal to 0, you will have phi, this is 0, and at x equals L, this is the free end, there is no moment, so you will have Gj delta phi by delta x at L this is my actual boundary condition. As usual, again you go put the separation of variable, that is P, you can write it as some capital P, Phi which is a function of xt, you put it capital P x and some q of t. Substitute, collect the q of t terms one side and then the p terms on the other side, and you will get the differential eigenvalue problem. So I am writing directly that differential eigenvalue problem. Differential eigenvalue problem this becomes d by dx of gj d dx equals minus omega square I p p, or which you can write it minus lambda I p with the boundary condition x equals 0, p 0 is 0 and x equals L, you will have gj d phi by dx at x equals L. So that is a fixed end, this is the free end. Now if I assume gj ip everything is constant, that is uniform properties, that is uniform properties. Then my equation will become gj d square phi by dx square plus omega square I p p equals 0, or I can write my solution as a some sign, because I can divide by gj, this is nothing but a second order differential equation, simple vibration problem. Okay, you will write square root of omega square ip over gj into x plus b cosine square root of now you substitute the boundary condition you will get when phi is 0, 0, that is x is 0, automatically this term goes. So your first boundary condition p0 0 gives me equals 0 implies b equals 0, right? Whereas now you take the derivative, because here d phi by dx, d phi by dx sine will become cosine, that should be 0 and a is not 0. So you will get the second d L dx. Okay, at the x equal to L, this becomes basically 0, implies that a cosine square root of omega square ip over gj L equals 0. That is my equation. Now here again you indicate that if a is 0, everything is 0. That's how non-trivial solution, you want this to be equal to some pi by 2, that's all. You will have, therefore your solution will be essentially square root of omega square ip over gjl will be n, where n running from 1, 3, 5, etc. Okay, that's all. And your solution is, that means you can get the frequencies and the mode shape becomes phi. This will become essentially any n equals some a sine. You are going to put omega square, this is any n, n pi. That means when equal to 1, omega 1, omega 2, omega 3, like that you will have lot of values. So I am going to put this itself as n pi by 2l root of Gj over Ip. Sorry, no, n pi by, n pi by 2l into x. Because this entire term is L you bring in, that is square root of omega square Ip by Gj, that is this term. So you will get, this is my mode shape, these are my frequencies. So I can plot them like, that's not a problem. Yeah. Or yes, like you said, you can also write n equals, what is that, 2 m minus 1 by, okay, into pi by 2, where m runs from 1, right? 1 is, what is that, pi by 2, 2 is 3 pi by 2, yeah. You can have it. So this is the shape, and this is the, what you get is, now you plot the mode shape. You will have sine wave, this is L, and the second one will be like this, and the third, so you will have omega 1 is pi over 2L root of Gj by Ip. Omega 2, 3 pi over 2L root of Gj over Ip. And omega 3 is 5 pi over 2L root of Gj over Ip. So this is for the torsion problem. Okay. So you have the complete, I would say, simplified problem solution, which we know how to solve now. In the sense, once the equation of motion is given, if it is simple, that is what the key is. Then you can write the solution, apply the boundary condition, get the frequencies and the mode shape, and you have plotted all. Now any general motion is a summation of all the mode shapes and with a generalized coordinate. This is for problems where you have exact solution. So we will learn next. Before I proceed further, I would like to finish one small section, and then we will go to how do you get approximate solution. Okay, because you cannot get exact solution for all the problems. Now your next question of how will I solve the response? Okay, that I will answer first. That is response of the continuous system, because you got the exact solution for this type of problem. What you do is, I will write the mathematical solution, because then you will understand easily the response of continuous system. Okay. Now our full equation of motion in operator form, please understand, this is W x comma t plus something W dot x comma t equals some f of x comma t. Okay, with the boundary conditions Bi Wi 0 and you had Bi Wi plus Ci W double dot x comma t on x and x equals 0 and L. This you can take I running from 1 to k. Here you use I running from k plus 1 to p and x equal to 0 and L. Okay. This is what we formulated our original problem. Now I have obtained exact solution, assuming that I somehow obtained the exact solution. That means eigenvalues, I got it. So you immediately go back and then your first step solution, you will formulate differential eigenvalue problem. The differential eigenvalue problem, I'll just for sake of formulate, that is you first get this and from here you will get your solution. I have obtained my solution, and you know one of the property of the eigenfunction is there that orthogonality condition. So what your that ortho normal condition, I will write it now. What is that? Over the domain minus plus summation I equals k plus 1 to p the other. These are the condition referring to orthogonality. Please understand that. I will explain now. S Bi W S ds is lambda S R and S run from 1, 2, 3, etc. See, please understand here I said delta Rs. Okay. This is shape function, eigenfunction R, eigenfunction S. They are orthogonal because when R is not equal to S, they are 0. But when R equal to S, what you do is you normalize it. That is what is called the normalizing the eigenfunction, such that this term becomes 1. Otherwise, it will have some value. Now, that is why you call it orthonormal orthogonal and also normal eigenfunctions. Okay. Suppose you say what type of normalization you can do, because there are several ways of normalizing it. Please understand. It is not that there should be only one way. Like I can take in the mode shape, tip deflection is 1. Okay. In the shape function, I am just drawing these functions. For a cantilever beam, I just drew like this. Okay. I am drawing like this. What value I will give? That it depends on that AR or CR values, C1, C2, C3. I can set C1 as 1, but then this is the shape. When I substitute that C1 as 1 here, I may not get delta Rs as unit quantity. I will have some finite value. On the other hand, I choose a particular value for the normalizing factor such that this is 1. Okay, that is another way of normalizing. That is why they are called orthonormal eigenfunctions. Suppose if you say, oh, if I don't normalize it, what will happen? Nothing will happen. Only thing is that corresponding value will get multiplied everywhere. Okay, so it is not a. There are various ways of normalizing the functions. One of them is this condition. Now you see, I have solved the eigenvalue problem. I know these are my normalizing conditions. I go back and then I got all the eigenfunctions, and I'll write my solution like this. This is what expansion theorem. Okay, expansion theorem. What I am doing is I am writing my W, which is a function of x comma t, as s running from 1 to infinity W of s, which is x, and eta s, which is a function of time. Okay, this is what we assume first. We split that into space and time variable. Now I am combining and writing, and I got all the eigenfunctions. Now my aim is to solve for this. Okay, I take this, substitute in my equation. Okay, when I substitute in my equation and then I integrate, because I have to apply the orthogonality condition. Okay, what I will do is, how many unknowns, how many generalized coordinates I have? I have infinite. And you know that I have infinite eigenfunctions. But I will not really solve for infinite number of equations. I will set it to a finite number. Usually in vibration problems, sometimes people take about 7 modes, 8 modes. Sometimes people may take about 20, 30, 40 modes or 50 modes. In an aircraft, actual aircraft analysis, they take somewhere around 60, 70 modes. Okay, some may take a little bit more, because they say even though the higher modes may not really contribute, they say their estimation of aerodynamics is better if I include all the higher modes, something like that. That means you can have more number of modes. You don't go to infinity. But normally in the helicopter rotor blade, we take about 6 modes, 6 or 7 or 8. But that's all. That means our entire continuous system is now converted into only 8 degrees of freedom or 10 degrees of freedom. Okay, so this is what is called, you can call it modal analysis, you may call it also. So the expansion theorem allows you to write this, and then this you substitute in your equation, use the orthogonality condition. So when you use the orthogonality condition, what you do is, when you substitute, you will get summation s running from 1 to infinity L W s of x eta s t plus summation s 1 to infinity capital M W s x eta double dot s t equals f of x comma t. F of x comma t is the external loading, which is your aerodynamic load. Now pre-multiply by WR. Okay, pre-multiply by WR of x and then integrate. Okay. When you do that, what will happen? You are putting WR here, WR here, WR there, and you are integrating over the domain, over the length of the wing or over the area of the wing. Because if it is a 2D, you will have two dimensional. This is a single, that's why X along the length of the wing. What will happen is WRLWS is here. WRLWS equals lambda S delta RS. This will go that side. Okay. Similarly, for the mass term, you will get this part that will go that side. Then what will happen to these two terms? These two terms are CIWS into eta double dot. You come here. BI, or you can say BI is a function. No, there is no I here. BIWS plus CIWS. In the sense WS, there is a into eta S double dot. That is nothing but 0. Okay. This is the boundary condition directly. That is why what will happen is these terms will actually drop out. Okay. So you substitute this as it is. If you put it, maybe I erase this part and write it here. You will get like this: summation S running from 1 to infinity delta RS minus summation I running from K plus 1 to P WR CI WS BS into eta double dot T, but maybe I will put this here. Okay, eta S double dot T plus summation S running from 1 to infinity, you will have delta RS lambda S minus summation I K plus 1 to P integral WR BI WS DS into eta S T equals integral WR F of X comma T D domain. R running from 1 to infinity. You will have infinite equations basically. Now you see, you look at this, WR is common here. CI WS eta S double dot. BI WS eta S. That is BI WS eta T is CI WS eta double dot, because this is the second derivative. Automatically this term will cancel out. Okay. Leaving behind very simple equation which will look like this. So that is why the boundary condition will come here to make sure that those terms cancel out. What will you get? Because these two terms go off and R running from 1 to infinity. Wherever S becomes R, okay, you will find that is 1. That means S should be replaced by R. So you will have eta R double dot T plus lambda R eta R equals integral WR, okay, f of x comma t. This is my equation. Okay. And these are my, please note, f of x comma t is my external loading. WR is the shape function or eigen function in the arc mode. Multiply that, that is the generalized force for the arc mode shape. So you have running from again 1 to keep on go, so many equations. Okay. Now if you want the initial condition, if you say that what is my initial condition I should use for eta r, you may ask, you know here what is the initial condition, right? You can always apply the orthogonality principle to get eta s. Or in other words, what you can do is I can take this, get the solution, substitute back here and use the initial condition. That is another way. Or else initial condition directly, knowing this, you can always get the initial condition from the orthogonality relationship. Okay. I will not go into the details of it because this part is supposed to have been the background when you come for the aeroelastic course. Okay. Now you got the general form. How do you get the equation motion, and then how do you really go to the response solution? Solving this is a simple second order differential equation. Each one is independent. Please understand. Each eta r is a generalized coordinate. It is independent. Please solve. Only thing is, to do this, you must know WR. And lambda r will come. Now you see the natural frequency, the corresponding mode shape or the eigenfunction. They come in this in the response calculation. Okay. This is what is done in the aeroelastic problem. Now you know that I need to know only this. That is the aerodynamics part. But one more thing which you have to know is, if I can't get exact solution, what do I do? Okay. That part I will